Okay, in this video segment, we're going to be talking about error and how all measurement has error. So anytime you go into a lab or you're making a measurement, it doesn't matter if you're using the most precise tool that we have, the best technology, or the worst and oldest piece of equipment that's possible out there. Every single measurement has error. There's no such thing as a perfect measurement. There's no such thing as being exact in the world of science. So we have to deal with this error to the best of our ability in order to minimize it. Now, for scientists, what that means is using some of our skills in terms of estimating. So within error, there always is an estimate for that last digit. Okay. So if we take a look at the screen, what we see here is if I tell you that this line is 0 and that line is 10. Okay. One line is 0, the other line is 10. We're able to estimate between those two lines. So if we get a line that pops up right there, and I say, what is the blue line? Okay. For you to tell me 0, or for you to tell me 10, you know is incorrect. You know that it's more than 0, you know that it's less than 10. But we actually have a better ability than that even. We can actually say to a reasonable amount of accuracy where that line sits. So take a second, look at the line and say, where do I think this sits in terms of between 0 and 10? Now once you've done that, you may have said 5, you may have said 6, you may have said 7, maybe 8. But if you look at it, it's pretty obvious it's either half or a little bit closer to the 10 by looking at it. So we know it's not below 5, and it's really kind of in between there. So maybe 5 to 7 would be a range that I would probably accept. Most people will say on there. 8 would be too close to 10, and 4 would be in the other half of 5. So somewhere between 5 and 7 would be our range, probably of what people say in terms of this. And if you go out and survey 100 people, they're probably going to give you, the answer of anywhere between 5 and 7, all of them. Now, is it perfect? Absolutely not. But to tell me that that line is 6, let's say, for example, say, okay, the line is 6. To say that is actually better than saying it's 0 or better than saying it's 10. So we have to be able to estimate between lines on our measuring tools. Now, it does not get rid of our error, but it does actually allow us to minimize it, and it's also better for us than to just start rounding things randomly. Okay. So if you need to know, there are the actual lines spaced out evenly. To give you an idea that yes, we are pretty good at our brains of breaking it down into 10 pieces. Now, anything more than 5 or 6, you probably couldn't tell me. You couldn't tell me that the line was at 6.5 or 6.8 because we don't have the ability really to break things down into 100 segments, but breaking things down into segments of 10 is pretty good for us. We can do that really well. So again, the estimate could be either between 0 and 10 in the ones column. You couldn't give me a tenths place here or a hundredths place here because you really can't estimate past that one digit past the measuring tool. If we take a look at this idea of error, we have to be able to actually calculate error in our measurements. So we have to be able to take what's going on and take our experimental values and then compare those to our accepted values and then calculate what is the amount of error that we actually have in these different labs we do. So if we take a look at our equation for calculating percent error, so our percent error, the absolute value of our experimental data minus the accepted. Sometimes this is called the lab data versus the known or the correct data. Then you divide it by the accepted. You always divide by the known because you want to have the error based off of what the known value is. So if you flip these two around, it really doesn't matter because it's absolute value. But you can't flip this one around. You have to always divide by the accepted or known value. And then you take it times 100 to get a percentage. Okay. So if we take a look at Bob and Frank again, Bob and Frank, they had their numbers. And if we look back, we remember that the accepted value for this was 5.58. So if we want to calculate the percent error for Frank, what we would do is we take the experimental, which is the average of 5.52, subtract away the 5.58, take the absolute value, divide by 5.58, take it times 100 to get a percentage, and we get 1.08%. So basically, he has really good data here because we're less than 5%. We're almost at 1% error, which is really high quality data for this example. Okay, so this is calculating percent error. That ends this video segment, and we'll move on to another one. Thank you.